Testing. Okay, all right.
Can I take you out to that side? Yeah, can I take you to that side?
Okay. Hello, hello. Happy sunny Wednesday. The sun is out, and look at how many of you are here inside at 3:30 on a lecture. I'm so proud of you. Okay, we're going to try out Slido. I will fully tell you, yes, maybe I'm a professional software engineer. Maybe I teach computer science, but technology is terrifying. So we're going to see what happens with Slido. So I think I published a thing. Can y'all try to log in? You can either go to slido.com and put in that event number, or if you go to the course website, you could click that link, or maybe that QR code works from where you're sitting. I don't know. It feels like it shouldn't, but maybe it does. And if somebody can get in and you can see a live question, could you give me like a thumbs up so I know that the thing works? We're not going to do the question right now. This is mostly so that we don't waste this time a little later once we actually get going. Is the TA thing working at all? Can any of you see it yet?
Not yet.
Okay. You got in? Yes. Okay. Thank you. Okay. Well, theoretically, this is, I'm always going to put I guess we have to do like a different Slido every single day. So I'll always put the new Slido on this front page here. You'll notice that once we really get into the course, I like to start off with like a discussion question or a warm-up problem. So I'll always have it up on the screen. But just so you know, I think it has to be different every day. Did it ask you for an email? Yes. Okay. Please put in your UW email. That's how I know you're the one that answered these things, and we can do that nice like participation credit thing. Also, I don't know if it says it from your purview, but the Slidos are always going to be open. I think the Slido default is like open for 3 days or something. I might even decide that's too narrow. So I'm probably going to make it so that every Slido is open for a week. This is mostly for those of you that are watching this on the recording. You don't actually physically have to be here to get your participation. Just watch the lecture and answer the Slido at some point, at least within a week. I think that's what I'm going to do. Okay, cool. That was also me a little bit vamping as we all sort of trickled in and found our ways. Let's maybe actually get started on this thing. Okay. Here's our agenda for the day. Great. Okay, some announcements. So things are officially live, and based on the interaction, it looks like some of you have found them. First of all, I was told a couple hours ago that the Canvas rostering system across UW is down. So if you cannot access Canvas right now, it's probably not you. It's some other bug. Sorry. Let's hope someone somewhere is fixing that. But remember, the only thing on Canvas is grades and the Panopto recordings. But the course website is live. It has our calendar up to date. And our wonderful head TA, Maya, has posted your P0 assignment and all of the setup steps. That assignment is mostly a 123/143 review. It's literally some problems I picked from Practice It that I think are relevant to what we're going to do in this class. So if you're sitting here wondering, I haven't done Java in a minute, am I going to be uncomfortable in this class? This is the assignment that you do in order to assess how you feel about it. This assignment you will also find is much shorter and less complex in the coding we're asking you to do. Because let's be real, the hardest thing to do is set up your environment. So the other real goal of P0 is to get you to download the JDK. That's how you actually write Java on your computer. And download IntelliJ. That's the IDE, or Integrated Development Environment, we're going to use. If you are coming out of the 1, 2, 3 sequence, you probably only ever used Ed, which means you didn't have to have Java or a separate program on your computer to write code. Welcome to 300 levels. We're moving on from that. But we know it can be kind of tricky to get all that set up. You also have to set up Git. That is how you are able to accept the starter code from us and to collaborate with your partners. So there's a bunch of detailed instructions and like click here and screenshots and all of that good stuff on the course website. And our wonderful head TA Maya is going to host some how to get set up office hours on Friday. So I encourage you to today or tomorrow go and attempt this setup so that on Friday you can go and Maya can help you maybe, fix anything that went a little weird. We will start official office hours on next Monday, and we will carry forward on the office hours tab of the course website. You can find where all the office hours are. If you're coming again from intro, we don't have like an IPL that's staffed all day. We have a collection of TAs that are themselves also students. So I asked them when they can make themselves available, and that's when they could. So we are going to appreciate our TA's busy schedules and work with it, but we'll see how the schedule works as we go. Please do take note that each of the office hours might be in a different location, so you do want to check on the calendar where that specific office hour is taking place. I will also take this moment in time to say there are 2 computer science buildings on this campus. Capitalism, computer science department. And so there is, I can't believe I'm going to refer to it now as the old computer science building. That's the one that says Paul G. Allen Center for Computer Science. It's the one that's like brick. Are they both brick? Is that distinguishing? It's the one that's attached to the ECE department. That we are going to lovingly refer to as CS1. The one across the street with the cafe in it that says Bill and Melinda Gates Center of Computer, the orange one, thank you. I'm pretty sure the orange is terracotta because it's environmentally friendly. Yes, we stand. That one is called CS2. I say this now because I get so many emails from students that are like, I'm out front of your office, but there's someone else here. You're in the wrong building. Cool. Section also does start tomorrow, so check your MyUW. Ooh, sorry, just remember we got an email pin. And so you will get to meet your wonderful, you might have 1 or 2 TAs depending on how the section assignments worked out. Again, section attendance is not graded, but that is where you get to do all of the practice, and a lot of the stuff I'm going to be talking about, I'm going to only be able to sort of give you the high level of the algorithm or give you the idea behind what you're attempting to do. Section is where you sit down and practice it in community with one another, and we know that's the secret to doing well in this class. Again, another one of my little data analysis shows that the type of students that fall under that 2.0 line, one of the other things they tend to have in common is not going to section. So do with that information what you would like. Does anyone have any course administrative questions? Cool. Great. Okay. Let's learn some stuff. Let's do it. All right. Okay. So in the last 7 minutes of lecture yesterday, I rambled off some very quick definitions for you about this thing called the ADT, which is a thing you've already been using, though maybe we didn't call it that in the intro series. And what I'm really trying to do here is to help you make a distinction between the design of what you are asking for functionally and the implementation of how you accomplish those functions. And if you remember, we learned about Barbara Liskov. She's the one that invented these things. This is the key abstraction that we are here to discuss in this course. So we will always talk first about what do you need your code to be able to do. That's sort of that ADT. ADT examples are like list, queue, stack. And then the data structure is how you actually go about implementing that thing. So like that's the array or the nodes that accomplish that functionality. Any questions on that review stuff so far? Cool. Great. So we are going to learn a lot of ADTs this quarter. As we learn an ADT, I will introduce you to what the functions they encompass are, and then we're going to learn a few different ways to implement them. Now you will meet some ADTs for whom there's kind of only really one data structure we use to implement them because the other ones are gross, but that doesn't mean you can't implement them with anything. We just, as we write code over time, we've all come to realize, like, oh, guess what? Priority queue is really convenient if you use a heap, right? That kind of thing. So list, set, map, stack, queue, and even priority queue, those first ones, I actually do expect to be familiar to you. So to just sort of like dust off those intro cobwebs, a list, we're going to talk about that in a lot of detail today. That's an ordered sequence of elements. A set, that is just an unordered collection of stuff. It's really good at telling what's in the set, what's out of the set. Set theory, haha. Math matters, as it turns out. A map, you will also hear me refer to that as a dictionary. That's when you have a unordered collection of pairs, where you have a key and a value. The reason we kind of call it a dictionary is I think of it like language, like an English language dictionary, where the key is the thing that's maybe in a sorted type of order so you can get easy lookup. Like if I asked you to go look up a word, you would go alphabetically in the dictionary to find the page that it's on, and then the value, the thing you're trying to really learn or pull out of that data structure, that's maybe the definition. So those things are a collection of pairs. We've got stack. Remember, a stack is a very specific way to order elements. The stack is that first in, first out kind of thing. We'll go over this again, but I like to think of it, and I feel like, I'm sorry if this is a very American reference, but we used to have those really sticky, plasticky lunchroom trays in school, and they were always like in a stack, and at the bottom of the stack was a spring, and the wonderful lunch staff was always cleaning that top one, so the top one was always wet because somebody had just used it, and then we'd washed it and put it back on, and the one at the very bottom was always kind of sticky, because like, unless you get all the way through them, you don't see that one at the bottom very often. The queue, that's like the line at a bank, first in, first out. You'd be pretty offended if the bank used a stack order of addressing customers, right? So queue, that's like queuing up to wait for anything. And then a priority queue is very similar, except instead of ordering by time in which you added things, we use that comparable interface to determine what should come first or not. And we'll get into a lot more detail on all of those, but those things I just sort of rattled off there are what I sort of expect of you to have already been exposed to. Does anybody have any clarifying questions on those? Cool. Also, I will take this moment in time to say, my understanding is that the Slido has a Q&A feature. Yes, thumbs up from the TAs. And so if at any point I stop and say, are there any questions? And you're like, how could you possibly ask me to raise my hand and make noise in this giant room of people? You can just go type your question on Slido, and the TAs right here can also answer you digitally. So, yay. However you have questions, please feel free to surface them. The two at the bottom here, graph is not really an ADT. I'm sorry for those. It's like kind of an ADT. It's kind of a structure. But that's a really important way of organizing data that we are going to get into. We're going to spend 3 weeks of this course on it. I do not expect you to have been exposed to that yet, but you're going to find it's my favorite part of the course. So get ready. I have so many dad jokes. Okay, and then disjoint set is our final one. It is like if priority queue is a more specific type of queue, disjoint set is like a more specific type of set. It's actually a set of sets. So we're going to learn a few new ones there. Cool? That's your little roadmap for where we're going. Okay. Oh, great. Questions. Cool. Okay, I am also now going to attempt to click over to the Slido thing, not my whiteboard. Let's see. I can do this. Aha, audience Q&A. There we go. Look, it doesn't look like there's any questions. Is that true in here? There's two. Oh, there's an archive? Oh, what a great question. Why didn't we use Poll Everywhere again? I used to use Poll Everywhere, but you couldn't have the Q&A feature while I did the questions. Oh, thank you. Oh, wow. Okay, thank you for, that was not helpful. Okay, like I said, we're trying out the Slido thing. I'll get better at it, team. Okay, yeah, I'm sure the TAs put a really beautiful response in there, so I appreciate it. Okay, let's actually dive into what we're going to be doing mostly today. We are going to be doing a deep dive into one particular ADT, the list ADT, probably the one you've used the most. Spoiler alert, the one you will probably continue to use the most, the list. Okay, so what do we need to know about any given ADT? I gave you that one line. It's like an ordered sequence of elements. I like this sort of drawing here. We've got, like things coming in. They've got, ascending indices. You can get something based on a given index. So I can pop in and say, hey, what's stored at index 0? That's the very first thing. Hey, what's stored at size -1? That's the thing at the very end. Hey, what's stored at, 4? That kind of thing. So that's get. You can set, meaning you can transform one of those things. You can append, which is this one here, adding on at the very end. You can insert, which sort of stuffs something in between elements, which means that any element that comes after it gets sort of shifted backwards. You can also delete. So if you delete something in the middle, that means everything kind of shifts forward. And then you can also get the size. So you can see this is some kind of pseudo-codey looking method headers. This is kind of how we define an ADT. Just like how we would define an interface, we sort of start with just those method headers. I haven't told you how to implement any of these things. I haven't said, guess what, size should be a field that you just return, right? I don't care. Maybe you loop over and count every time you run size. Don't do that. It's bad design, but you could. And so this is what I mean when I talk about this ADT. I'm talking about the functionality first. And you can see here on the bottom right, here is a way that you previously could have used a list in the Java framework. And I'm sorry, we're missing the word string here. One thing I want to make sure that you notice here is we've got the ADT name list. Then we've got these things I'm going to call angular brackets, and between those angular brackets is the type. In this course, we are now going to graduate from that intro style of objects where you had linked int list, array int list, and those were lists that could only store that type of information. Now we are going to be using something called generics, so that when we declare these objects, we got to also tell them what type of information they're going to store. And you got to have that angular bracket syntax. You will be using that. I will be posting examples. I will be calling it out, but that is something that unfortunately they don't teach you in the intro courses, so just keep an eye on that type of syntax. And then you can see there, we're using some of the methods. So this is what it's supposed to do. Let's talk about some of the ways you can write code to accomplish those things. So here in our little Husky gold box, that's my symbol for the ADT. These Husky purple boxes, those are the data structures. And so right now we can sort of think of two general approaches to implementing the list ADT. One, where we can see here the state, and remember state and behavior, those are the two words we associate with an object, where state is just sort of our fancy abstracted way to say fields. For the fields of the array list, we are going to have an array. Usually we call it data, something like that. And then we probably have a field called size, because what we're going to do is we're going to start with an array, and it will initially start with some default size, but we are going to represent that sort of though it's an array of a certain size. If we haven't added anything, the size is 0. So we need a separate size field to tell us how much space of the array we have used so far. And as we add things, we're going to add them to the front of the array, and we're going to use size to kind of know where in the array we've filled up. Once we completely fill up the array, if you remember, arrays can only be a singular size. We can't grow and shrink arrays. Once we make them, they're just that size. So once our size hits the capacity of the array, that means we need a new array that's bigger. We got to copy everything over and do all that sort of stuff. I'm going to go into more details about how the logistics of implementing these features with an array work, but compare that to the linked node, linked list structure, and that is where instead of this sort of block of elements all stored together, we have this object called a node. In intro, it was called a linked int node, I think. You define a node. That node class probably has a field for data and a field for next. And then you have these sort of little objects that sort of daisy chain together like this. So any given element sort of points to the next node in the sequence. I will pause here and say in this course, we are going to be talking pretty exclusively about singularly directional linked lists. There are such a thing as doubly linked lists where each node has a pointer both to the next and the previous. It's pretty convenient, and in some cases it works really well, but it's a lot messier code-wise. So you should be aware that that type of thing exists, but for the most part we're going to be coding this type of linked list, which hopefully looks pretty familiar to you from intro. The other thing to keep in mind about linked list is that in order to change elements or move them around, all we got to do is change those references, right? I kind of think of them as like train cars. We can kind of unhook them from each other and hook them up back up again, so on and so forth. Also, we typically have a field front that points to just the first node in the collection. Some of those doubly linked lists would also have a field called back that would point to the back. Again, depending on your design, that could be very helpful. But for us, we're just going to maintain a front pointer, and we're just going to have singularly linked lists that go to the back. And then you know you're at the end of the list if your next field has a null value stored in there. I'm hoping this is all, again, mostly review. Any questions so far? Let's get into some of the nitty-gritty then. Okay. So let's talk about implementing insert with these two different types. So let's say we have an array list in this state. So right here you can see we have an array, an underlying array with the capacity of 4. But we're only using 3 of the spots. I know that because the size field, number of items, says 3, which means I still have more space to fill up. So when I call insert, if I do call insert of the value 10 at index 0, what's going to happen is I'm going to insert that item. Wait, what's 0? Oh, hang on. Okay, sorry, hang on. My animations might be a little funny there. Okay, I don't know what just happened with those animations. Oh, wait, there it goes. There we are. Sorry, I could see them now. Okay. So if we are going to insert the value of 10 at index 0, what's going to happen is I am going to need to make space. Right now, the element at index 0 is 3. So that space is occupied. So in order for me to get this value 10 into that space, I'm going to take the 5 and I'm going to copy it into the 3 index. And I got 2 5s, so I can replace the old one. So I'm going to copy the 4 into the 2 index. And then I've got 2 4s, so I can copy the 3 into the 1 index. And I've got 2 3s, so I can replace that original 3 with the value 10. So anytime I do this type of insertion in arrays, I've got to do this type of shifting thing. You know, it's sort of like, you're standing in line and you got to kind of bump your way past every single person to get to your seat in the movie theater because you just had to go pee, right, or whatever it is, and you kind of bump everybody along the way. It's a little annoying implementation-wise, and also something to keep in mind when we're thinking about the runtime. Now, comparatively, if we look at, and then we update the size, cool. If we look at how we would insert 10 at index 0 in the linked list doesn't keep track of its own indices. So whenever you are dealing with a linked list, you sort of have to do the counting yourself when you're implementing with the nodes. Because the nodes don't know what index they're at. You know what index they're at by counting from front forward. So in this case, thankfully, we know, hey, index 0 should be the thing directly counted to front. So I'm just going to scooch that one right in there. And I will have its next field point to what was previously pointed at by the front. So I don't have to jostle the rest of the things. I can just sort of pop that node right in where I need it to be, and then I can update my size field. Any questions so far? Okay. Let's talk about delete. So let's say I want to delete the item at 0. Well, in the array context, You might be inclined to say, well, like, oh, maybe I just tell myself, like, ignore the thing at 0 so I don't have to do that shifting. Nope, we can't get away that nice and easy. We need things to be in the precise index they're supposed to be at in the array list, because the real value of the array is that, like, give me an index and I'm going to pop right in there. So if I want to delete the thing at 0, that means that the thing that's currently at 1 needs to now be shifted into that location. There we go. Okay. Shifted into that location. So what we did there is, as you can see, we started to do copies. There we are. So we copied the 5 into index 2. We copied the 4 into index 1. We copied the 3 into index 0. And then we decrement the size down to 3. Now you might be like, Casey, there's still like that extra 5 kicking around back where it used to be. I don't care. It's dead to me. That's just like the garbage over there. So as long as I keep my size field updated, I don't care if there's anything stored in those other indices there. The size is what determines what's sort of like in play within the array. But again, I had to do that like jostle thing. Everybody kind of had to get up out of their seats and like move over so that everybody landed where they were supposed to be in the appropriate index. Now you can imagine with the linked list, if we call delete, all we got to do is just skip that node. If you remember, Java has this magical helper called the garbage collector. And so as long as you say something like front equals front.next, what that does is it means we sort of drop anybody holding on to that reference to the first node. We just sort of forget it. I like to think of nodes as balloons with strings, and you just sort of let go of the string, and the balloon floated off into some magical memory location, and then the super helpful garbage collector at some point that you don't have to care about came by and like cleaned it up within your computer. So remember, the way you delete nodes for linked lists is you just let go of the references, or you skip the nodes is another way to think of it. Again, nice in that we didn't have to jostle all the other nodes in order to accomplish this. We just updated front to sort of skip what it was originally pointing at. Cool. Great. Okay. Now let's talk about append. So this is a situation, as you can see here at the top, I've got an array list that has an underlying array of capacity 4, and I have a list of size 4. If I call append of 2, what that means is I would like the value of 2 to be added to this collection, and I want it to come after the 5. But right now, there is no space in the array for that to happen. So like I mentioned, what this means is, because we can't grow the size of our array, we're going to make a new array. Convention states that we make an array double the size. And then we copy everything over. We're like, okay, well, like in my new array, 10 should be still in 0. 3 should still be in 1. 2 should still be in 4. 5 should still be a 3. And now we've got space for 2, and we can update that size field to 5. And now I've got 3 extra spots for when I want to append later. We do this sort of doubling thing because this is kind of an expensive moment, right? If we call append one more time, like let's say we append another item and it's supposed to now go what is in index 5, it would be really easy. We're just going to kind of pop it into that nice open spot. So sometimes append is like really quick, easy, convenient for us, and sometimes append is a pain in the booty. And in this moment, we've got to like copy things over, we're using extra space. And so because of that pain point, that's why we always double the array instead of say just like making an array of size plus 1. We only want to have to do this double and copy thing over so many times. So we're going to kind of sort of like ask for more space than we need right now, so we don't necessarily have to do this quite so often. The other question I usually get asked at this moment in time is, okay, well, like, what if I called remove, and I like removed all these items? Do I then go downgrade the array size? And convention states, no, we don't. The array list implementation, the list just grows. Because if the list is at one point this big, well, we might need that space over again and like making a new array and copying it over just to reduce the amount of memory that we're using is usually not the most efficient. So that's one thing to keep in mind when we're talking about this array implementation, is that we are always growing the array, but then if we say delete everything, we could end up with array capacity way bigger than we necessarily need. But that's sort of our trade-off with the array, is we're always trying to guess how much extra space we need to carry along with us. With the linked list one, if I call append of 2, well, I have a null pointer in the next field of the 5 that I just sort of plop a new node into. Great. But append means add to the end, and I only start with a reference to front, which means in order for me to know where to add this node, I got to have a loop that kind of just goes over every node, because I can't just jump to index 4 with the linked list. I got to actually start a pointer and move my way all the way over there until I get to the right spot so I can make a new node. It's I kind of have to walk down the line of train cars until I get to the right little hitch, connector, I don't know. And then you kind of add that extra node in. So what's interesting here is, though it looks really nice in my animations, there is a loop that's happening so I get to where I know I need to be in order to do that add. Cool. And then we update our number of items. Okay. Before I get into the scary stuff, any questions on the array versus node implementation of list? Yes?
So does the times increase exponentially if we always add the elements into the array?
Does the runtime increase exponentially if we are always appending into the array? Is that what you asked?
It's after adding thousands of elements, it will always double it.
I see where you're getting that sort of exponential piece from. You know what? What a beautiful segue. I swear that was not a plant question. Thank you so much. Let's talk about this in more detail. Okay, so our friend astutely was looking ahead to how we are going to, in this course, analyze our code. Now, in the intro course, it was mostly does your code work? Great. End of thought. In this class, welcome. I don't necessarily care even as much about how your code works. I care that it's efficient. I care that it's best designed. Now, there's a lot of different methods in which we can analyze code. This is all about the runtime. And when I say runtime, I mean sort of the time it takes for the computer to go in and execute all of your instructions. Now, the thing about that is, depending on how fast your computer is, how many programs you've got going on, what's happening within your memory system, the physical clock time can vary a lot by computer. So it's not very interesting for us to talk about it in amount of seconds that it takes to run. So instead, we talk about it in this type of mathematical sense, where we compare the runtime in relation to how many pieces of data we're running that code on. Because when we're running the code on, say, 10 elements or something like that in the class, it's almost always going to feel instantaneous to us. But we are now 300-level programmers, and we are going to be working with data sets so large that we're going to start to care more about their performance in terms of when we have thousands of pieces of data, or tens of thousands of pieces of data, or millions of pieces of data. And that's when you start to actually see the time it takes to execute things. So you may have had a brief introduction, and I swear you are going to be so annoyed with Big O by the end of this course, because we will not shut up about it. So if you don't understand it after today, don't worry. It's not going anywhere. But we think of this thing, I'm going to keep saying the word big O. That's sort of the terminology for how we classify the runtime into these different classes. So we sort of have these groupings of relative runtime efficiency. So our friend was asking is that kind of exponentially related to n if we keep doubling and doubling? Totally makes sense, right? Let's kind of walk through some of these classes, and then guess what? I'm going to ask you to assess all of the things I just talked about in a big O perspective. So the first complexity class we refer to as constant. The reason I keep saying big O is that's that notation, that column, the second column in. So if I want to say something is of constant time, I would write literally a capital letter O and then the parentheses, and then we just put the number 1. What that means is your code runs exactly the same number of executions, number of instructions, runtime, however you want to think about it, regardless of how many things are stored in your list. So, for example, let's say that with, you have some big collection of data, but I don't necessarily need you to look over everything in the data. I just need you to grab the thing that's at the very front. So you don't care how many things are left in the list, just grab the thing at the front. It's independent of how many things are already stored in the list, so it's constant time. There's no sort of factor of n in the model, which we're going to write a bunch of next week, for how many instructions are executed. So accessing the index in an array. It takes the same amount of instructions to get the item at element 0 versus the element at element 100 versus the element at index 10,000. I don't care, right? Diving into an array, you can just dive in based on the index. Doesn't matter how many things are stored in the array. That's constant time. The next one down, linear, or let's see. Yeah, I guess we'll do logarithmic. That's another runtime. That's where the runtime in relation to n sort of cuts in half every time. The way I like to think of it is binary search. Binary search, if you remember, is if I say give you a sorted list of elements. Again, let's go back to maybe our dictionary example. If I asked you to look something up in the dictionary, if you were clever about it, you would probably open up to the very middle and see what number, like letters in the alphabet you're at, and you'd be like, oh, is my letter earlier in the alphabet or later in the alphabet? And then you would look at that half, and you wouldn't have to keep flipping through pages for the rest of the half. And then you would look at maybe, like in the half that you're focusing on, you'd split that in half again, and then you would again sort of eliminate another fourth, and then another eighth, and so on and so forth. And so the amount of pages you're checking to find the word you're looking for sort of reduces until you find the thing. That's logarithmic time. That one I know can be a little bit harder sometimes for our brains to hold on to. We will get a lot more examples of logarithmic time. But we write that O of n, or O of log base 2n. You will often see I don't write the base. But in computer science, when I say logarithmic, I almost always mean log base 2, for those of you that are from the physical sciences. Then comes actual linear. That's one where the amount of instructions, the runtime, is directly based on how many things are in the list. A classic example, loop over everything in the list. Like, let's say I want you to find something in the list. And you don't know if that thing's in the list or not until, like, let's say it's not in the list. You got to look at everything in the list to determine it's not in there, right? So you're going to have probably a for loop that starts at the beginning and loops all the way to the end. So if there's 10 things, you got to look at 10 things. If there's 100 things, you got to examine 100 things. If there's 1,000,000 things, you got to examine 1,000,000 things. So the amount of time it takes to run grows linearly in relation to how many things are stored in the list. Then we've got a few more down there. Quadratic, that's n squared. So that's usually nested loops. That's if I'm like looking at the number at the very beginning and then looping over the rest of the list to compare it. And then I move to the next thing and I'm looping over the rest of the list and compare it. And so I've got that nested loop structure. Then we have quadratic growth. Any questions so far on this piece? I know I'm hand wavy. We're going to get some practice. Okay. Cool. Annoyingly, I'm not going to answer our friend's question because y'all are going to answer my friend's question. So I want you, and it should be live on the Slido, there is a quiz that's going to ask you to guess the class, the complexity class that each of the operations we just discussed falls into. So instead of fast and slow, I want you to think, how many instructions are we going to need to run in order to accomplish, say, accessing something, I think at index n, for example. Like if we are trying to get to the nth element, how many things do we have to examine in order to get there in the array versus the linked list? And then I think there's an insert. What happens? And remember, when we thought about how those things were implemented under the hood, remember in the array, sometimes you can just dive into the middle. Sometimes you got to do that shifting thing. And when you do the shifting thing, there's probably a loop involved, a loop that goes over the entire list. That loop's probably based on how many things are in the list. With the linked list, a lot of times we could just sort of throw something at the front, or we could just delete something. But don't forget, did we have to loop over that linked list to find where we were looking for? So I'm going to ask you to actually engage with the community around you. And let's be real, it's the start of a new quarter. Be the person in class you want to be. Turn around, introduce yourself, offer some pronouns, find that person that's sitting alone. I know how it goes, and offer your name. Maybe they'll offer it back. We're going to take a solid 3 minutes. Go ahead and discuss with the people around you, and then we're going to discuss the answers to this. And yes, the TAs are going to come around and answer any questions you have as you do it. Go ahead. I volunteered you, I'm sorry. All right, I have been informed that you can only answer the first question on the quiz. Is that true? Were there 4 or were there 1 question on the quiz that you could answer?
I just activated the second one. I don't know.
How do? You activated
I
it?
just did. I hit the arrow.
Oh, you have to do them one at a time?
One at a time. That's stupid.
I thought I was being so clever. It's fine. All right. All right, we'll come back together. I love all the discussion is music to my ears. Also, sorry, like I said, I'm learning this Slido. Apparently, you can only answer 1 question at a time. I don't know. We'll figure it out. Oh, okay, fine. We'll talk about it. Okay. All right, so time needed to access the nth element of an array. Does anyone want to raise their hand and tell me what they and their group discussed as the complexity class for that first one? Yeah, here. Sorry? O of 1, absolutely constant time, because, like I said, you can just say the index, and I don't care if it's index 0 or index 100 or index 1,000,000, you just kind of dive into the middle. So it's independent of how many enter in the list, constant time. What about the linked list? Does anyone want to raise their hand and tell me what they discussed complexity class-wise for that one? Yes?
You have to cycle through the entire list.
Yes, absolutely. I love how you said that too. You have to cycle through the whole list, right? You got to kind of have your own variable. You got to count until you get there. You got to cycle through. So that is linear runtime. So that will be a little slower. In the interest of time needed to insert at the nth element. Maybe shout it out. What do we think the runtime for that one is? Oh, I heard it. Yes, linear time, because we got to do that weird shifting thing, remember? And the shifting means I got to jostle everyone along the way. So I have a loop that runs over the list. What about for the linked list? What do we think the runtime is for that one? Oh, I heard it. Linear, yeah, because like, got to loop to where it's supposed to be. Even if we can just insert it where we want to be, we can't just dive in because we don't have indices. Now, I also asked these 2 questions at the back here, which I did not discuss with y'all. And in the amount of time we have left, I'm going to give you a teaser for what we will pick back up on Friday for, which is the amount of memory used. So previously, we were only talking about how many instructions ran. But when I'm thinking about how much space in memory I am setting aside to hold my elements, for the array implementation, does anybody want to raise their hand and maybe give me a guess as to like, is it exactly the same amount of space as the number of elements, or do I have like a little extra kind of hanging out? Yeah. Yes, absolutely. You have some extra space. So I kind of think sometimes wasted space at the end of the array, because it's like you got to have that array bigger and then you kind of fill it up and then you copy over. Compared to the linked list, we just make 1 node for every item. So we don't ever have that kind of empty space problem. Now, what about the space per element? But I've never asked you to think about that. So we've got the amount of space in memory that it takes for a single element in an array versus the object with the fields. Yeah, I have some thoughts? Yes. In fact, it is a tiny bit extra, but yeah, you can kind of think of it as like for every single value, you have to also store the next field, right? So you kind of have two pieces of information instead of a single element within the array. We are going to dive into that in a lot more detail on Friday. We're going to talk a little bit more about how the compiler partitions memory in the computer, and we'll have some design discussions. All right, thank you so much for being here, everyone. Try P0 so you can use those office hours on Friday, and go to section tomorrow and meet your TA. Thanks so much.